Hello, good morning, good afternoon, good evening from wherever you're watching this video from. And I would like to thank you so much for creating time to watch this video. My name is David Mwita, and I have been the trainer for this MPLS configuration series, where our focus has been and will always be to configure MPLS from scratch on Cisco and Huawei routers. On your screen is a brief bio about myself, a little something for you to be able to understand or know me before we proceed, especially if this is your first time watching my content. Then this will be very helpful for you to at least have a glimpse or a clue of who I am. Now, you can watch our other videos on YouTube. Just go to YouTube and search for Lifey Technologies, and there we have various videos that have been tailor-made for specific or very important networking topics like OSPF, BGP on different platforms that can be of help or importance to you as a network engineer, especially if you are a junior or aspiring to be a network engineer. The content there is tailor-made for you, so kindly create time and review or view our other videos that we have in Lifey Technologies. So another again, the channel is Lifey Technologies on YouTube. You can also contact us via the email addresses that have been provided to you. We'll be glad to get your reviews, get your ideas, or just to get to know what you would want us to produce or what you want us to handle next, which topics are of interest to you, and we will see how to share that knowledge, because in Lifey Technologies, we believe sharing is caring. So this is our fifth video. It was supposed to be covering MPLS L2 VPN configuration, specifically VPWS, Virtual Private Wired Services. But due to public demand, we would want to change and gears here and focus on MPLS label operations. Before we proceed, let's just familiarize ourselves with what we have been able to do so far. So we've done 4 videos already, and the ones marked in green are the key concepts or topics that we have been able to do so far. So the last video, which was video number 4, we discussed or concentrated so much on configuring MPBGP, and then creating customer VRFs, assigning those VRFs into or to specific interfaces connecting to our customers, and thereafter we were able to establish PE to C peering using BGP as the routing protocol, and we confirmed reachability for our CEs that belong to the same VRF, but they are geographically separated. So that's what we were able to achieve. We were supposed to tackle MPLS L2 VPN, as I've said, but it is important for us to understand how label switching actually happens inside our MPLS environment. In your production environment, you need to know how those label swappings take place, because without that, unfortunately, you will not be able to understand how MPLS works. So let's go quickly to our discussion today. So we're going to talk about MPLS label operations, and the key things that we will be able to do here is that we will be able to understand what those operations are, and where they take place, and what is their role or how significant are they within our MPLS environment. So in the MPLS data plane, packet forwarding is done using 3 fundamental operations, namely push, swap, and pop. Now, push can also be referred to as label imposition. Swapping can also be referred to as label switching. And lastly, popping can also be referred to as label disposition or label removal. These operations are executed based on the label forwarding information base entries as packets traverse the MPLS networks. Now, your router keeps 4 very important tables that you need to understand in the context of MPLS and routing in general. Number 1 table is at the RIB, routing information base. Number 2, the fib forwarding information base. Now, in terms of MPLS, an equivalent of RIB is LIB, label information base, and an equivalent of fib is LFIB, label forwarding information base. So lib or rib are your control plane, fib and lfib are your data plane. Okay, now number 1, let's talk about push. So what happens here is a label is added to an incoming IP packet, and then the packet becomes an MPLS labeled packet. This happens at ingress PE or our label edged router, and the reason as to why this happens is to map the packet to a forwarding equivalence class and determine its LSP, label switched path. So we need to determine which path that packet is supposed to use from your source to your destination. And what happens is that packet arrives to your PE, a label is imposed or pushed, and then that particular packet now ceases to become an IP packet, it becomes an MPLS packet. Number 2, swapping. Now, the incoming label is replaced with a new label, and this is done at P routers, and sometimes this can also be done at PE routers along the path. If I just draw something here, assuming that this is your topology, this is your topology, this is your topology. Let's add a couple of routers here, and then that is your PE, and this is your other PE. So they're connected to each other. This is your P, this is your P, this is your P, and this is your exit. Then maybe they combine here and become and exit via the PE there. Okay, so apologies for my bad drawing, but I want to demonstrate something. So this is your PE. Unfortunately, or assuming that this particular P route is not available, then your traffic will have to be forced to use this path here. Instead of going this way, it will come this way and then go this way before it finally arrives at your PE. Okay, that's why we are saying that it's not a must that this operation only happens on P routers. It can also happen on or at P routers along the path. Okay, so swapping happens at PE and PE routers, as I said, and each hop uses locally significant labels, and the path is maintained via label switched path LSP. I have a diagram that will be able to show you exactly how that happens inside our MPLS environment. So what happens is a label comes in as 100. You as the P routers or the ALSR, you look up your LFIB and find that that label has that label that is 100 is your local label actually. So you have to swap it with the outgoing or the remote label that has been advertised to you by your MPLS LDP peer. Okay. Then from there we have popping. This happens at the egress, and the MPLS label is removed and the packet goes back to pure IP forwarding or standard IP. It is done at the egress PE or penultimate hop. This is where PHP takes place, and we'll be discussing about PHP in our next slide. So what happens is that MPLS label comes in to your PE or your egress PE, and then the label is removed. The label is removed, and after that, the MPLS label that is removed. And once, basically, it's MPLS header that is removed. So if that header is removed, what remains is your normal IP packet. Okay, so that particular router decides that this is the end of MPLS, and therefore I'll have to send an IP packet to my CE or the destination without the MPLS header. A point to note here is that POP operation removes the MPLS header before forwarding the IP packet to its destination. So we touched about penultimate hop hopping. Let's quickly understand what it is. Now, the second to last router removes the label instead of the egress PE. Why? Because this reduces processing load on egress PE, especially this is important in MPLS L2 VPN, where we have double labels, that is the transport and the service labels. This is something that I think we touched on it in our last video, but we will also be able to understand what transport and service labels are. But for this case, I have a very small topology just for us to be able to know or get to understand how label operations take place, or how label switching happens within our MPLS environment. So the second to last P router will do the POP, and then the egress PE will receive the IP. And in the case of L3 VPN, it will receive an inner label. The transport label, which is the outer label, will have to be stripped off before it goes to the egress PE. Now, PHP is triggered using implicit null label, which is by default label number 3. And what is implicit null? Basically, it's used by the egress router to signal penultimate hop popping, and it never appears in the actual label stack. You not see it, but I think for the case of Huawei, we will be able to see that you can actually see the label 3 in the label stack. But for Cisco, I'm not sure about other vendors, but for Cisco, you are not able to see it in the actual label stack. Instead, the upstream router pops the label before forwarding the packet. Okay, so that has been an explanation on how MPLS label swapping, pushing, and popping takes place. Now, in this next slide, as you can see, I have a couple of routers here, R1, R2, R3, R4. For the purposes of this demonstration, I decided to go with Cisco routers, but our lab has Huawei and Cisco routers, just to understand what happens, because in Cisco, you can actually be able to control or define a label range. Even in Huawei, you can do a static label range, but I find it very easy how Cisco have been able to design their platform. So it's very easy for us to understand MPLS when we use their device. But once you get the concept from here, then we can go ahead and now jump into the virtual environment and see those labels in operation. So this is our MPLS service provider core. It has R1 all the way to R4. In here, we've enabled OSPF as IGP just to ensure reachability within our service provider environment, whereby R1 is supposed to reach the loopback interface of R4. The loopback interfaces are assigned in the format x.x.x.x, where x is the device number. So in the case of R1, you have 1.1.1.1, R2 2.2.2.2, and R4 4.4.4.4 as the loopback interfaces, and they are all /32 IP addresses. Okay, so like I mentioned earlier, your routers, especially the PEs, will keep not just the PEs, actually, the PEs and the P routers inside your MPLS environment. They will keep in the context of MPLS, they will keep two very important tables. The first table is the lib, which basically is your control plane, and the other one is the lfib, which is your data plane. Okay, now the lib is actually derived from your RIB, routing information base. That's where this table is populated from, and your lfib is populated from your forwarding information base fib, that is the data plane in the normal IP routing. So difference is RIB, fib, that is your normal IP routing, but fib, lib and lfib, that is your MPLS tables that you need to focus on. So what happens is that, for example, let's just assume that we have this user here who is in this particular network, and PC4 is in this particular network. Okay, so we want to achieve reachability. so that PC1 and PC4 would communicate or ping each other. That's what I mean by reachability. Okay, so what we'll be able to do is we will be able to configure. We've already configured MPLS and OSPF. Everything is running, and then we can do BGP between R1 and R4, and then advertise this route to BGP, this route to BGP, so that R1 can see this prefix in its routing table, and R4 can see this prefix in its routing table. And thereafter, on R1, we'll be able to try and attempt to ping this PC, and vice versa. On R4, we will try and attempt to ping this PC. Okay. So before we do that, let's see how label operations happen within our MPLS service provider. So as I mentioned, your router will keep these two tables. Number one, the lib, and here each MPLS enabled routers will assign a local label to all the prefixes in their routing table, except the directly connected prefixes. For example, these ones here and these ones here would not have a local label for R1. For R2, this here and this here, including the loopback interface, will not have a local label. And for R4, you not have a local label for this, you not have a local label for this prefix and for the loopback interface. So that is how it works. So another thing to note is that labels are assigned to prefixes and not individual or host IPs. But in case you have loopback interfaces like we do here, your loopback interfaces are /32s. Those ones will be assigned labels, and they will be treated as prefixes, not host IP addresses. Okay, so that is what you need to understand before we proceed. And then the other thing is, just to emphasize, directly connected networks they will only be given an implicit null, not an actual label, and we'll be able to see why an implicit null. Okay. Another thing is the local label, which is the incoming label in this case, is used to receive traffic, whereas the outgoing label or the remote label is used to forward traffic. That is something for your notes, and it's important for you to understand that. So let's proceed. So we've already said directly connected prefixes, no labels for them. That's why you can see for 192.168.1.0/24, we have a null there. For 12.1.1.1.0/24, we have a null. All these are /24s. I haven't included the loopback interfaces just for simplicity. So all our prefixes are /24s. And so this is the local label. So since 23.1.1 are not directly connected, these three here are not directly connected, then our router will actually assign a local label to each prefix, as you can see from here. And then equally, R2 being our neighbor, our LDP neighbor, they will have to also send us the label that they have assigned to those specific prefixes that we have in our rib in R1. So as you can see, since 192.168 is not directly connected to R2, it has imposed or pushed a label to it. It has assigned a label to it. But this one is directly connected to R2. Then the label is not there, so we get an implicit null, or you can call it implicit null. Same case to this particular prefix. It's directly connected, therefore you get an implicit null. But other prefixes get assigned labels, and they get advertised to us in R1. The same thing happens to R2. Okay, so directly connected interfaces, directly connected networks, no label, you get a null there. And this is how it happens across our MPLS service provider up to R4. So as you can see, R4, 34, 172, those are directly connected, therefore you get a null. And then R3 will send us their labels to us. So in R3, this is the local label, but it becomes a remote label when it lands to R4. Okay, as you can see for this prefix here, it's 300, which is the local label in R3. Okay, so once the lib table has been populated, now we can populate the label forwarding information base table or entries from that lib table. So again, this is your control plane and this is your forwarding plane or data plane So moving forward, as we said, your lib table will contain all your prefixes. The only exception is the directly connected networks will not be assigned a label. You'll get a null there. But when we are populating our label forwarding information base, we will for local labels, we will not have the directly connected networks in our LFIB. As you can see, they are not here. We don't have 192. We don't have 12. Equally, in R2, in our LFIB, we don't have 12 and we don't have 23. For R3, we don't have 23 and we don't have 34. As you can see, it's not there. For R4, we don't have 34 and we don't have 172. That network is not, those networks are not in our LFIB. So it is important to note that LFIB does not have directly connected networks. It doesn't. That is only found in your LIB. And the commands to show LIB in Cisco and Huawei are different. We'll be showing you that when we get into the lab. So what happens? 23.1.1, the local label assigned there is 120. What we get from R2, which is the remote label, is null because it is connected to R2 directly. So we get a null there. For 34, the local label assigned by us is 130, and the remote label assigned by R2 is 230 to that prefix. 140 is assigned by us, 240 is assigned by R2. You get the idea. So I've been able to define ranges. So this is the range from 100 to 119. This ranges from 200 to 299. This ranges from 300 to 399. The range here is 400 to 499, just for simplicity. Okay, so let's proceed. For R3, you can see the local label assigned to our prefix 192 is 300, 12 prefix is 310, 172 is 340. And since we are going now, this is where I explain something. As you can see in lib, we have two remote labels for R2 and R3. Two remote labels. One that is advertised by R1 because we are neighbors with R1. Then the one that is advertised by R2 because we are neighbors with the R3. For R3, we have again two remote labels. One that is advertised by R2 because we're neighbors with them, and the other one is advertised by R4 because we are neighbors with R4. But when we are populating the LFIB, your router actually checks the FIB, forward information base, and sees, for me to get to this particular network, which way should I go? Okay, so let us take this 192.168.1.0/24 network or prefix as an example. So we are in R3. So R3 asks itself a question, a very simple question. Now, I got this particular prefix advertised to me maybe via OSPF. Not maybe, we have OSPF, so this is advertised to me by OSPF, so I have it in my routing table. Therefore, I will have to assign a label to it, label 300 in this case. Okay, now if I want to go to this prefix, which way should I go? I'm in R3 here. This is R3. and I want to go to this prefix. Which way should I go? What should be my exit interface? And in this case, your exit interface is E01 Ethernet 0/1. That is your exit interface to this prefix. Therefore, you'll only record the label that has been assigned to you by R2. And if you go to R2, the label that has been assigned to that particular prefix is 200, and as you can see, it is in R2's LFIB 200. Therefore, this is the label that you will only have to record in your LFIB in R3. That's why we have 200 here. Okay, I hope that is clear. Moving forward, let's take another example just in L3 and understand why we have a null here. So the prefix 12.1.1.0/24, the locally assigned label is 310. But again, for us to go to 12.1.1.0 network, which way should we go? Again, our exit is it's E01. That's our exit interface. So this direction. Therefore, again, we are going to assign the label that has been advertised to us by R2, who is our directly connected MPLS neighbor. So if you go to R2's LFIB, what does it have for 12.12.12? As you can see, it's not here. That's where you get a null. If you check its lib, the 12.1.1.0/24 gets a null as the local label because it is a directly connected network to R2. Let's take another example. In this case, let's use let us use R2. Let's use R2. So R2 wants to go to 172.16.1, for example, that prefix. The locally assigned label is 240. Okay, so if I'm at R2 and I want to go to 172, this prefix here, which direction should I go? This direction. What is the exit interface? This is the exit interface, E01. And therefore, I will only be able to record the label that R3 has sent to me. And if you go to R3, for 172.16.1, the local label here is 340. Therefore, R3 will send me 340, and I will record it here. So when we're doing the label switching, we just have to check the local label and then what is the remote label, and that is what determines what operations to do. So for example, in this case, R2 will swap to 40 to 340 and send that particular packet to R3. R3 will look up its LFIB and find that it has, yes, indeed, it has 172.16.1.0 network, and the local label is 340, and it will say this is my label. I'm the one who assigned this label to this particular network or prefix. What should I do to this label? And then it will look at its LFIB and say, I am getting an implicit null from R4. As you can see, R4 is giving me an implicit null. Therefore, what I'll do is I will remove the label and forward that IP packet to R4 as a normal IP packet. I hope that is very clear. So let's take a last example and then we can be able to understand it better. So let's focus ourselves, let's focus on this particular segment, in this particular segment here, okay? And let me change the color of our pen. Nice. So the packet comes, so PC1 want to go to PC4, for example. So that packet will come with an L3 header and L2 header here as an Ethernet. Okay, so it will go to R1. R1 will receive it and sees that the source is 192.168.1.1, and then the destination is this particular IP here, which is here. Okay, that's supposed to be 40, but it's fine. So the network is actually here. So R1 will look up its table the LFIB and see if it has an entry for this particular prefix, and it will find that entry right here. It's 140. Therefore, it will say my local label is 140. What I'm supposed to do to this particular packet is remove that 140 label and impose or push to 40 to it before taking it to R2. So R2 will receive the MPLS packet. It will examine it, and the focus is actually the destination network. It will say, I am receiving this particular MPLS packet, and the label here is 240. Let me go to my LFIB and see what 240 corresponds to as my outgoing or remote label that I'm receiving from R3. And that particular remote label is 340. Therefore, R3 will swap to 40 with 340 and send that particular packet to, no, sorry, R2 will swap to 40 and 340 and send that particular packet to R3. R3 will receive it and it will see the label as 340 for this particular destination. And then it will go to its LFIB table and say, for 340 and for this particular prefix or network, what I'm supposed to do is remove the label because I'm getting a null or an implicit null message from R4 here. Therefore, before I send it, I will just strip off this particular label and then send that IP or that packet as an IP packet without any MPLS header. So R4 will receive it and checks its. So since R4 has received a normal IP packet, it will not examine its LFIB table. It will not. It will actually now get to examine its routing table because it is receiving an IP packet, a standard IP packet without any MPLS header. So it will examine its routing table and find that this 172.116.1.0 network is actually a directly connected network in its routing table, and to go to .4, the exit interface is this particular interface here. Therefore, it will send that particular packet down to PC4. So that is how MPLS label operation takes place. And then again for review, there are only three. They are push, swap, and pop. So to understand popping better, we did say that penultimate hop popping, that is your PHP, penultimate hop popping, happens at the last router before the egress PE. So this is our P, this is our P, this is our PE. So the last router that is connected to our PE is here. And we said the reason as to why PHP is done is because it reduces the overhead or the load for our PE. Imagine our PE is connected to so many customers, and it has to do both popping and removal of IP addresses. So it will be overwhelmed. So to do that, it will get the help of our P router here, which will do the PHP. Basically, what it will do, it will remove the label and forward a packet like we've seen here, that this packet is sent to R4 without any MPLS header. Therefore, if it receives an IP packet, it just goes and looks its routing table, or for this particular VRF, for example, if it's VRF Amani or VRF ABC, it will look up its table and find that the exit interface is E01, and then it will forward the packet as a normal IP packet. So that is the importance of PHP and where it actually takes place. With that said, now it's time for us to go to our live virtual environment and talk about and see those labels in operation, that is. So for review, this is a Cisco device, this is a Huawei device, a Cisco device, a Huawei device. As you can see, Huawei devices have different icons and Cisco devices have different icons. I've just done Cisco routers here and change their image or icon to look as if it's a Windows PC. But this is just for just for visuals. You get to visualize how this network is and understand it better. And that is our prefixes. Our loopback interfaces are already configured. MPLS is up and running, but before that, OSPF is also up and running. If you can quickly confirm that, show MPLS interfaces. You can see we have enabled interface on that particular MPLS on that particular interface. We can actually see if we have a neighbor, OSPF neighbor, show IP OSPF neighbor, and we do. What about R3? No, R2 is a Huawei display current configuration OSPF. Sorry, I have to type it correctly. We have configured OSPF, as you can see. We have a neighborship display OSPF peer, and yes, we do. We are neighbors with 1 and 3. R3 is Cisco. Show IP OSPF neighbor. We are neighbors there. That's correct. And then lastly, R4 being Huawei, the command is display OSPF peer brief, and we are neighbor with R3. Perfect. We can see the routing table, display IP routing table. And as you can see, let's filter to OSPF. You can see we're getting these prefixes. Let's go to R3, show IP route OSPF. We are good there, and let's confirm R1, show IP routing, OSPF, and we're good. Lastly, let's confirm, show MPLS. Let's confirm MPLS. Now, I promised to show you the command to confirm the LIB and LFIB, label information base control plane, LFIB data plane. So to confirm control plane or lib in Cisco, the command is show MPLS LDP bindings. As you can see, we have our directly connected interfaces here. That is our loopback interface. As you can see, for the local label, we are getting an implicit null, but for the remote binding, that is from R2, we are getting that label. And for 12, let me show you all the directly connected. For 12, as you can see, we are also getting an implicit null. We as R1, we're not imposing any label to that. But as you can see, for the case of this prefix, we are actually imposing or adding a label to it or assigning a label to it, and we are getting a remote label from R2, and that's the label. For 192.168.1.0 again, we're getting an implicit null because for local label we're not going to assign any because it's directly connected. So that's how you check the LIB, the lib. How you check the LFIB is show MPLS forwarding. You can see locally connected networks are not here. We only have those that are not locally connected, and we can see we are assigning labels to them. That's how we confirm in Cisco. In Huawei, the command to check your lib is display MPLS LDP LSP. So you can be able to see all your prefixes here. But for 12, not 12, for 34, there is no local label. For 172, it's not even here. And for 4.4.4, we are assigning it an implicit null because it's connected to us. That's where you're able to see that there's a point that I said. Let me go back to it. And this point here, the implicit null never appears in the actual label stack. Instead, the upstream router pops the label before forwarding the packet. But I mentioned in Cisco, this is true, but as you can see in Huawei, you can actually be able to see that particular label assigned right there. This is how you confirm the lib. How do you confirm the lfib? The command is display MPLS LSP, and here you can see it has the directly connected, not directly connected, but it has the loopback interfaces. And for 4, you can see it's implicit null as the local label. And for these other ones, you can see we are assigning the correct labels, and therefore there we are good. Now from here, are we able to trace 1.1.1 and see how it goes? So caution, in Huawei, when you just do the normal trace to a destination, for example, it will not automatically show you the labels. It will show you the hops, as you can see, but it will not show you the labels. To ensure you're getting the labels, what you do is you use this command, trace at LSP IP, then you give your IP address, and then you give a subnet mask. There now, you're able to see the labels that are being either imposed or swapped. So let's quickly examine this one here to understand. So let's give ourselves some space. And let me bring my notepad. Bring my notepad here. There you go. Good. Okay. So we are going to 1.1.1.1. Okay. So let's see how label pushing and swapping and popping takes place. So for us to go to 1.1.1.1, our ingress router is R3, as you can see clearly here. Okay. So we go to we go to R3. If we go to R3, you can see from R4, the label assigned to that particular prefix, this prefix here, is 302. So we go to R3. Then from there, for R2, the label assigned to 1.1.1 is this particular label. Okay. And then when we go to R2 now, it will see that for me to send this package to R1, I will have to give it an implicit null. So R1 will do the popping before it sends that particular, as you can see, there is no label here, so it will do the popping. Sorry, R3 will do the popping and send a normal IP packet to R1, which will send it to our loopback interface connected to R1. Okay, so this label here, let's go to R3 and see that show MPLS forwarding. So label 302 is here. So R3 will receive the packet and it will look up its lfib and see that for the local label 302, I should swap it with this label here before I send it to R2. And that's what happens. So R2 swaps 302 with this particular number and sends that particular packet to R2. Okay, so R2 will look up its lfib, display MPLS LSP. So R2 will look up its LSP and find that for the label 48120, which is right here, the outgoing label is 3, which we have already discussed is an implicit null. Therefore, before sending this packet to MPLS packet to R1, I will have to remove the label. So what R2 does is it does penultimate hop popping PHP and sends to R1 a normal IP packet. That's why if you go to, so for 48120, and then it does the popping before sending that particular packet to R1. So R1 goes to its LFIB and find, no, it doesn't go to its LFIB. Sorry guys, it doesn't go to its LFIB because it has received a normal packet from R2. Therefore, R1 will only just look up its routing table, okay, which is show IP route, and indeed it is connected and it's there. It's loopback interface. That's how it does. So let's trace 172.16.1.0 this is dot 6.6, yes, from R1 before we went up. So trace 172.16, sorry, 1.6. Let's see how it works. So we first of all go to R2, of course, then we go to R3, then we go to R4, finally we go to user 6. Let's see. So we can see we're going to R2. Going to R3, again as an MPLS labeled packet. We're going to 4, that is R4, and finally we should be hitting user 6. So let's quickly examine this again. Let's grab this and put it here. Okay. So remember I told you we have configured BGP. We've configured BGP between R1 and R4. Let's quickly show you that. Show IP BGP summary, and we are getting those prefixes. That prefix, that is. So the prefix we are getting here is 172.16.1. So we're getting this prefix from our next hop, which is 4. So we are tracing to this. So R1, this is a normal IP. So R1 will check its routing table and be able to establish what is or who is sending this particular prefix to me. So show IP route, show IP route, and you can see we have R4 here because it clearly says our next hop is R4. So we have R4 here in our routing table. There you go. And what is our next hop? 12.1.2. But remember, we also have R4 because it's not directly connected to us. We have R4 in our lib. Okay, quickly confirm that. Show MPLS forwarding table. R4 is there in our lib, and our local label that we assign to that particular prefix is 102, and this is assigned and sent to us by R2. So let's quickly examine this. So we're going to 172.16.1.6. That is this particular guy here. But before we reach there, the one that has advertised this prefix to us, this 172.16.1.6, is R4. And how do we get to R4? We use the label, this label. So that particular packet is sent to R2 as an MPLS packet with the label 48,122 assigned to it. Okay, so R2 receives it. After R2 receives it, it sees 48,122 in its LFIB and its local label. Therefore, the operation here is swap this particular label with 300 and send it to R3. That is what it does. It swaps it with 300, sends it to R3. Let's go to R3. R3 looks up its LFIB. That is, you can confirm by this command here, show MPLS forwarding table. It looks up its LFIB and confirms that for R3, for label 300, what I should be able to do is pop label before sending it to R4 via this particular next hop. Okay, so R3 receives it from R2. It examines 300 and sees that this is a local label for me, but for the outgoing label, is you pop label, meaning no label. So remove the MPLS header. So that is what it does. It removes the MPLS header and forwards the normal IP packet to R4 without any MPLS label. R4 receives it. Since it has received a normal IP packet, it will not check its LFIB table. It will rather check its routing table. And then it goes on, so we go and say display IP routing table for 172.16.1.0, and it says yes, I have that particular entry in my routing table because I received an IP packet, not MPLS packet. And since it's an IP packet, I will have to check it inside my routing table and establish or determine that or decide that this particular prefix or network is known to me, and I am supposed to send it out to this particular interface, that is E0 Ethernet 101. Then it finally reaches to goes to R6. So guys, in a nutshell, that is how MPLS label pushing, swapping, and popping takes place. That has been our time, and I would like to thank you for taking time to watch. Please comment, share your thoughts, let us know what you're thinking about our content, and what we can do to improve, or what topics you'd want us to do next, just to make you a better network engineer. Because like I said at the beginning of this particular presentation, sharing is caring, and the more I get to share this thing with you, by the way, you are also helping me to grow and be a better network engineer. Because before I produce a video or any content on any networking topic, I have to do research and dig deeper, and that particular research helps me, to have the knowledge that I can share with you guys. So until next time, thank you so much, take care, and God bless.